This is a question on energetics. It also ties in with one of the required practicals, and it's going to have to be done in a slightly different way because the graph section does not lend itself very well to doing it from the screen. So I am going to show you both parts of the question, but I'm then going to recommend that you follow the video through to see how the graph is completed to calculate delta t, and then continue the calculation from there. So this is the first piece of information, and you're going to be using this graph. And this is the calculation that you are going to be carrying out. So I'm going to go back to the graph and we're going to look at how you do this. You'll notice that we have got temperatures taken up to 3 minutes, and then again from 5 minutes onwards, we didn't take the temperature at 4 minutes. That was the point where the reaction took place, where the magnesium ribbon was added. Now, the way that you work through a question like this is you are going to draw two lines of best fit. You're going to draw one line of best fit which shows the trend before the magnesium was added, and you'll see that I've extrapolated that forward, and that's indicating what would have happened if no magnesium had been added. I've also completed the cooling component, and I've extrapolated that backwards. You'll notice that I've ignored where the temperature's still been going up because we're more interested in the rate at which it cools down in the lab where we're doing the experiment. And I've extrapolated that back beyond 4 minutes, and it's absolutely vital that both of these lines do go to the 4-minute point where the reaction took place. So you'll notice it's very unclear actually, but I've put a green line going up at 4 minutes, and that is the theoretical maximum temperature rise that would have been achieved. We're looking at how quickly this cools down. We're looking at what the consistent temperature was in the room at the beginning. And what we're essentially assuming here is what the temperature would have gone up to if all of the magnesium had reacted immediately, instantaneously, with absolutely no heat loss. Now, when I do that, I get to a delta T value of 17 because I've got a maximum temperature there of 40 and I started at 23. Now you've got your delta T of 17, have a go at the rest of the calculation, and when you're ready, unpause and move on. So in terms of mark allocations, we've got 2 marks for the graph. We're then going to use Q is MC delta T. I'm going to substitute the figures in. The M is 10, and that's because we're doing this in 10 cm cubed of solution, which we assume to have a density of 1. That will always be the case. The 4.18 is always provided, specific heat capacity, and our delta T we calculated on the graph is 17. Once we do that, we get to a value of 710.6 joules, and I've got my third mark. Now, to work out kilojoules per mole, I first of all need to know how many moles of magnesium there were. So I take my 0.24 grams, I've converted it from milligrams, and I divide by 24.3, taking me to 0.0098 moles and my fourth mark. Now I've got my joules and I've got my moles, I can do joules divided by mole to get my delta H, and I get to a value of 71,923.07 joules per mole. Now I want it in kilojoules per mole, so I'm going to divide that by 1,000, and I've made it to mark 6. But I've got to be mindful that the answer needs to be given to an appropriate precision. And based on the data that we've been provided with, that should be 2 significant figures, so we get 72 kilojoules per mole.